So let's talk about some more techniques for solving systems of equations. So consider, again, the set of coupled first-order differential equations that we had looked at in a previous video. So x1 prime is 4x1 minus 3x2, and x2 prime is 6x1 minus 7x2. And just as we have done in other cases, we could solve these using eigenvalues, but there's actually another way as well. And so let's learn a new technique, and this technique involves converting a system of differential equations, of coupled differential equations, into one differential equation, which is of a higher order. So first, let's solve equation 1 for the variable x2. And so moving things over, we get x2 as this. So now take a time derivative of this equation. So you get x2 prime is equal to 4/3 x1 prime minus 1/3 x1 double prime, a second derivative. So now plug these expressions for x1 or x2 and x2 prime into equation 2 to eliminate x2. And so the left-hand side and the right-hand side now only involve x1 and its first and second derivatives. Now if you simplify this to just put it in kind of standard form, then you get x1 double prime plus 3x1 prime minus 10x1 is equal to 0. So notice that this is a second order linear differential equation. So we can solve this equation for x1 using our usual techniques, like using a characteristic equation. So let's do that. Let's say that x1 goes as e to the pt, and so p squared plus 3p minus 10 is 0, which gives us p-values of 2 and negative 5. So that means solutions for x1 look like c1 e to the 2t and c2 e to the minus 5t. So we've got our solution for x1. Now we can plug this into our expressions for x2 to find the solution for x2. So x2 is related to x1 by the function and its derivative. And so if we take x1 and plug it in, and then plug in x1's derivative here, we get some complicated looking expressions, but okay, we can simplify this, and we simplify it and we get 2/3 c1 e to the 2t plus 3 c2 e to the minus 5t. So let's summarize. The solution of the coupled differential equations that we started with, x1 prime and x2 prime is equal to these things. Previously we solved it using eigenvalues, but if we solve it using substituting in and solving for a second order differential equation, we get a solution which actually is equivalent to the previous solution that you would have gotten using eigenvalues. It just looks a little bit different. Okay, let's look at another example. So let's solve the system x prime is equal to minus 2x plus y, and y prime is equal to minus 4x. So again, we can turn this into a second order differential equation by solving equation 3 for y. And so we get y is equal to x prime plus 2x, and then take a derivative of this. So y prime is equal to x double prime plus 2x prime. And then plug these values for y and y prime into equation 4. And equation 4 only involves y prime actually, so the left-hand side becomes x double prime plus 2x prime, and then the right-hand side is still minus 4x. So moving the 4x over, this is again a nice second-order linear differential equation. And we can solve this again using the characteristic equation. So let's do that. So with using a characteristic equation, we say x goes as e to the pt. So p squared plus 2p plus 4 must be equal to 0. So p values are negative 1 plus or minus the square root of 3i. So our solution for x looks like this complicated expression with our complex values up in the exponential. Or of course we know we can write this in a real way as e to the minus t cosine, or a cosine of square root of 3t, and b sine of square root of 3t. Okay, so that's our solution for x of t, but we want a solution for y as well. And we can get that using our relationship between x and y. And this gets a little ugly because we have to take a derivative of x and then add in 2 times x. So the derivative involves 2 terms shown here, and then you also have the 2 times x of t as well. It doesn't look particularly nice, but okay, we can simplify this by collecting the cosine and sine terms. So it looks like e to the minus t, some constant times cosine of square root of 3t, plus some other constant times the sine of square root of 3t. Okay, and so this is what we would say our solution is to our coupled differential equations. Okay, so we can always do this, though, in reverse. So let's say we had a second-order differential equation. Well, we can convert that into a system of first-order differential equations. So that's another technique that is worth knowing. So we can convert some second-order linear differential equation, well, and actually it doesn't have to be linear, it could be any second-order differential equation, into a system. So consider x double prime plus 3x prime plus 25 over 4x is equal to 0. And the way we convert it, we say let y be x prime, so y prime is x double prime. So we can just rewrite this differential equation in the following way. So this original differential equation, substituting in, becomes y prime plus 3y plus 25 over 4x is equal to 0. So if we want to rewrite this total second-order differential equation, what we've really replaced that with is two first-order differential equations. X prime is equal to y, and y prime is equal to minus 25 over 4x minus 3y. These are totally equivalent ways of writing this differential equation. All right, just for fun, let's solve this system of differential equations now using eigenvalues, as if you would for any other system. So we write x prime is equal to ax, where our vector x is xy, and our matrix is given here from our system of equations. So we want to find the eigenvalues of our matrix A, and so we get an determinant that we need to evaluate here. And that ultimately reduces down to the equation lambda squared plus 3 lambda plus 25 over 4 is equal to 0. And that has solutions of lambda is equal to minus 3 halves plus or minus 2i. Note that if all we care about is the solution for x of t, and we don't really care about y, remember y is just x prime, then we don't really need the eigenvectors. We only need the eigenvalues to find the solution for x of t, which is good because finding eigenvectors is kind of tedious. So the solution for our x vector, if you write it in terms of the unknown eigenvectors at this point, would look something like this. For some eigenvectors, we don't know what they are, but we don't really need to know what they are if we just want the solution for x of t. So x of t will just be some constant, e to the minus 3 halves plus 2it, plus some other constant, e to the minus 3 halves minus 2it. Or writing that in terms of real functions, you get a damped oscillation with frequency of 2. So why would we go through all of the trouble of rewriting our second-order differential equation in terms of a system? It seems easier to solve it as a second-order system. The eigenvalue and eigenvectors method is just much harder than it seems like it's useful. Well, the reason is, certainly for second-order differential equations, it's not the best way to write it as a system. But the fact that the eigenvalues and eigenvectors are harder than the characteristic equation is really only true for a second-order system. For third-order and higher-order systems, as you sometimes get, using eigenvalues and eigenvectors is really the only way to go. It's the best way to find the solution that you're after.